Hi, and welcome to my YouTube channel. I am Algebronx. I present lessons on Algebra 1 and Algebra 2. So subscribe to Algebronx for your at-home lessons while we're in this at-home school closing crisis. Today I'm going to present a lesson on the zeros of quadratic, and this is geared for Algebra 1. So we have been discussing quadratic functions and what they look like, in terms of their equation, as well as what they look like graphically. So we talked about how to find the vertex of the function, which is the turning point, when the vertex is a minimum and when the vertex is a maximum, depending on the sign of the lead coefficient. We have discussed factoring these quadratics, in which we're going to go more into detail today, and finding where the function's decreasing, where the function's increasing, and the range of the function, and as well as the domain. So all of these concepts are going to come together again, and we're going to have our focus more on finding the zeros of the function. So finding the zeros of the function, a zero is otherwise known as a root of the function. Okay, so zeros, and it's the same word whether it's an ES or just an S. They're the same as, so AKA roots of the function. So basically a zero of the function means where the function equals 0. Where the function equals 0. So when do you have a function that equals 0? When f of x equals 0. And we know that f of x is the same thing as saying where y equals 0. So a large part of what we're going to do is we're going to solve these quadratic functions for y, make sure that y equals, and then set them equal to 0. Let y equal 0 and then solve them. Because the zero of the function is where the function is 0. Now, graphically speaking, where is this? Well, if you're on your x-axis, there's your y-axis, anywhere along here, the function equals 0, because you're neither up nor down from the function. So the zero of the function, or the roots of the function, are the places that are on the x-axis. And for those students that confuse it and worry about, like, oh, am I going to remember that? I usually do a word association. So the word association today is roots. If I were to plant a flower in the ground, the roots I would plant here on the ground, and the roots would grow underneath. So the roots of the function start where the flower meets the flower. So the flower goes up, the roots go down. Right here are the roots of the function. This is where the roots start, right there on the ground. So just a little word association that sometimes helps us remember that roots are zeros and they're on the x-axis. Okay, so we're going to start with our first function, and we're going to graph it and look at this both graphically and algebraically. For the most part, on your regions, you have to solve for the roots algebraically. So you have to set it equal to 0, you have to factor it completely, and you have to show that the factors are each set equal to 0 and solve for them. So we're going to start with the function y equals, or x squared plus 2x minus 3. And we're going to look at this from a graphing standpoint first, because that's what we've been doing all along. So let's draw our xy axis here. And I'm going to first figure out where my vertex is. Okay, so let's do that by finding the axis of symmetry. So if I want to find the axis of symmetry, it's x equals negative b over 2a. A is 1, b is 2, a equals 1, b equals 2. We don't need c right now in this little formula, so I'm just going to plug that in. Negative 2 over 2 times 1, and negative 2 over 2 equals x equals negative 1. Okay, so that's our axis of symmetry. The axis of symmetry is the vertical line that goes through the vertex and divides the parabola into two equal parts. So at x equals 1, when I draw this dotted line, I'm going to have the axis of symmetry, and I'm going to label this, I'll label it here at the top, x equals negative 1. Okay. Now on either side of that line are the roots, and I want to figure out exactly where eventually, but first I'm going to find what the vertex is. So to find the vertex now, I take this x value and plug it in and find f at negative 1. The function at negative 1 is negative 1 squared plus 2 times negative 1 minus 3, which is 1 minus 2 minus 3, which is negative 1 minus 3, which is negative 4. So when x equals negative 1, y equals negative 4 leads me to my vertex, negative 1, negative 2, negative 3, negative 4, at negative 1, negative 4. Okay. Now the lead coefficient of this is 1, and up to this point I've been telling you to use that graphing method where if the lead coefficient is 1 and this is not a parabola that's been stretched or compressed in any way, that the next 2 points are 1 above and 1 over, and this is using the idea of the parent function and reflecting it from the parent function, which again, if you remember that the parent function is the one that sits at the origin, the vertex sits at the origin, and this is a shifted parabola because now we know the vertex went down to negative 1, negative 4. Okay, so now with that said, the next 2 points, think to here, when 1 was squared, it equaled 1. So it went from here up 1 over 1 in both directions. When x is 2, 2 squared is 4, so it would go up 1, 2, 3, 4, and over 2 in both directions. So my zeros of the function would be this point and this point, according to how I am generally graphing that. Either A, using my table on my calculator, or using that little trick where we know how it's shifted from the parent function. So with that, now I'm going to draw a parabola that represents this function, and we're going to now relate the factors to these specific points. Okay, so those points have coordinates 1, 0, and negative 1, negative 2, negative 3, 0. And I want to confirm that by factoring this quadratic and relating them to these zeros. So the zeros of my function have these coordinates, okay? So now I'm going to take my, erase this, I don't need this anymore. I'll take my function and set it equal to 0. Set it equal to 0. So open up 2 sets of parentheses, ask yourself the question, is there a GCF? No, they don't have anything in common, there's nothing to factor. And x squared, you form by x times x. I need factors of a negative 3, that when added give me 2. So factors of a negative 3 when added give me positive 2 means I need a plus 3 and a minus 1 there. And then we have a property called the zero product property, which says if 2 things multiplied, a times b equals 0, then a and or b equal 0. So you set each of those factors equal to 0, and you solve for x. So subtract 3 from both sides, add 1 to both sides. X equals negative 3 and x equals positive 1, which is confirmed by looking at the graph and seeing those points in their places, respectively. So Today's focus is going to be on this process, but it relates completely to the graph. So the graph is going to confirm the results of the algebra, because more times than not, you're asked to solve for the zeros or the roots algebraically. So we have to show that algebra, and then you can confirm it by graphing, okay? And we can do that using our calculators in order to confirm those roots. Okay, so let's do another example. Okay, so now this time I'm just going to give you some factors of a polynomial. 2x plus 1 and x plus 4. Okay, now these are factors already. Each of these represents a factor. This is called a binomial factor, 2x plus 1, and this is a binomial factor, x plus 4. Neither of those parts can be broken apart unless they were a GCF that I can factor out from that binomial. But right now it says it's a binomial factor. Now, if the problem says find the zeros of the function, zeros of the function is where y equals 0. So you set it equal to 0, the factors equal to 0, and I call this a t-chart because it looks like a giant T, and each factor is set equal to 0. Subtract 1, cancels, 2x equals -1, divide by 2, x equals -1/2, and minus 4 from both sides, x equals -4. Okay, so in this case, I was given the factors, making my life a lot easier. These are your solutions. So solutions are -1/2, -4. They're my x solutions for my roots. And the coordinates of those points are -1/2, 0, and -4, 0. Okay, so these are the x-intercepts. These are the zeros of the function. Also is called the solutions to the function. Okay, so this was generally an easy one. Now, what about if you have an example where you have a GCF, for instance, x squared minus 6x, function equals, right? So y equals. Okay, now, in this case, this doesn't factor in the traditional open two sets of parentheses because there's a GCF with each of those terms. So, examining the terms, they both contain an x. A GCF is the lowest power of the variable in common. So the x comes out, and then you've got x minus 6, and you set those factors equal to 0 because, again, we're solving for where y is 0. Now, this is a factor. X is a factor by itself, and x minus 6 is another factor. So there are still two factors, but this is a really simple one. So again, you make the t-chart dividing those factors up and set each factor equal to 0. And this factor is already solved. X equals 0 when y equals 0. Therefore, this parabola will go through the point 0, 0. Okay, that's a point. A lot of times students miss that and they forget that that actually can be one of the places that the graph goes through. So we have to remember that. Add 6 to both sides, x equals +6. And so the two solutions here are 0 and 6 in our solution set notation. And this coordinate is 6, 0 if we need to state the coordinates of the x-intercepts. Okay, so that was a different type of example where you've got a GCF. And I have a few more examples. So practice a little bit of factoring now. I'm not going to make it too easy and give you the factors, but you have to be able to factor. Okay, so let's see. This next one is going to be f of x equals 4x squared minus 81. Okay, what type of factoring is this now? There's a binomial. There's a minus in between. You examine your first term, examine your second term. This is a perfect square term. Square root of 4 is 2, square root of x squared is x. This is a perfect square term. Square root of 81 is 9. So this is the difference between two perfect squares, which factors into conjugate pairs. So recall when we were practicing factoring, we had the conjugate pairs where if a plus b, the other one was a minus b. Those are conjugate pairs. And they multiply to give you a squared minus b squared. So that's the situation we have right now. And we're going to have this broken into conjugate pairs. So solve for the zeros of the function. 0 equals 4x squared minus 81. Step 1. Step 2, 0 equals, let's factor it into the conjugate pairs. So 2x, giving you 4x squared. 9 and 9, giving you times, multiplying to give you 81. And then 1 is a minus and 1 is a plus. And it doesn't matter, you could switch those. You could put that one plus and that one minus. Because remember, multiplication is commutative, so you can swap the order with no repercussions. It just stays the same, okay? And now we're gonna make a t-chart. Each factor equals 0. So we're gonna add 9, and then we're gonna divide by 2. And so x equals 9/2. Please leave it that way. A lot of students don't like fractions. Fractions are fine, there's nothing wrong with them, they're numbers, and you gotta get used to working with them. I'd rather you leave an answer in fractional form. And when we divide by 2 here, we get x equals negative 9/2. Okay, so our solutions are negative 9/2, comma 9/2. And that's it. So coordinates 9/2, comma 0. Negative 9/2, comma 0, the x-intercepts of the function, roots, zeros of the function, and you're done. Okay, in this next one, it's a traditional trinomial, so we're just going to practice f at x equals x squared plus 8x plus 12. And for those of you that like that x method, when you're factoring, we need factors that give you a positive 12 and add up to give you a positive 8. So you're thinking, what numbers multiply to give you 12? Some students like to list the factors, 1 times 12, 2 times 6, 3 times 4, and then think, well, positive means they both have to be plus plus or minus minus. In this case, you look down here, and that sign tells you that they have to both be plus plus. Okay, so two numbers when added give you 8. I think it's pretty obvious. 2 plus 6 gives you 8, and 2 times 6 gives you 12. So we need a plus 2 and a plus 6, and then 0 equals the function, because we're looking for the zeros of the function. 0 is equal to the factors x plus 2 and x plus 6. Make the t-chart, set each factor equal to 0, and I think by now you're kind of getting the groove of it. If it's plus 2 in the factor, then your value is going to be minus 2, and this is going to be negative 6. So the solutions are negative 6, comma negative 2, and we have the coordinates negative 2, 0, negative 6, 0. Okay, and you're done. All right, let's try one where there's a GCF and binomial factors as well. So they come up a lot. In fact, they probably come up more often when you're asked questions, especially on the regions. They like to throw in a little curveball, and that seems to be the curveball they throw in. Okay, so we have the function y equals x cubed minus 10x squared plus 25x. Okay. So upon inspection of this, my 10 came out funny. Upon inspection of this, they all contain an x. So that is a GCF factoring first. Take the x and factor it from the polynomial. So y equals x is going to go on the outside, and x will